Hello, everybody. This is Zachary Molinero, and today I'm talking about programming assignment 4, which is dealing with Banker's algorithm. And the main thing I'm going to talk about today is how to really deal with safe sequence display for my upgrade. That's what I went for, and also to see whether a resource request is considered safe. So let me get started here with my AI um explanation. Um, Jesus, Quest keeps the system. Okay, perfect. Perfect. Okay, so basically, this is what the AI is talking about. It's mainly just talking about the safety algorithm. The idea is before the OS actually hands out resources for a request, it pretends to grant it and then checks could every process still finish if there was a worst case scenario. And it does this by keeping a work array, which starts as a copy of whatever is currently available. So it could be, a banking request, as let's just keep it going with the banking theme here, such as deposits, withdrawals, anything else that you can really think of when you're at a bank. Um, Let me see what it says here. The bank. Yep, well, in a safe state before actually allocating the request. First checks does not. Yep, and then currently available. If both conditions are met, it temporarily pretends to. Yes, perfect. Exactly what I just said. Performs a safety check. It creates a copy of available and repeatedly looks for a process whose remaining resource needs can be satisfied with the currently available resources. If such a process is found, and execution releases all of it. Yep, perfect. So pretty much what it's gonna do is that it's gonna keep going through all available resources just to keep making sure if I could there you go. And then yeah, it continues until all processes can finish or no additional process can be satisfied. If every wow, there you go. Every not not some of them, not a lot of them, if every process can complete successfully, the system is considered to be in a safe state and then the request is granted. If at least one process cannot finish, the system would enter unsafe state. So pretty much um the yeah, that's the best way to say it. Allow the fake allocation is going to be rolled back. So, um, kind of like I don't know what's a good example. Let's say someone tries to make a deposit of cash and the cash and it's not that. Let's say someone withdraws. Let's do the withdrawal thing instead. If someone tries to withdraw, let's say $500 when they only have $300, the temporary thing goes to them, the 500, and then it's rolled back and then denied because they don't have $500 in their account. They have $300. So this pretty much ensures that the system can never go to into a deadlock kind of state. So this actually connects back to what we covered in the lecture about deadlock avoidance. It's different from deadlock prevention because we're not eliminating one of the four conditions ahead of time. Um, Instead, we're allowing request, but checking case by case. So checking process by process until every single process is satisfied. Um, so pretty much since we're taking more time to check the request like by each and every single process, it makes deadlock impossible. Like it's impossible because we're checking every single process. If we were not to check every single process and just let it run rampant, yes, it will absolutely 100% run into deadlock. I think that's all for this section. Let me just check my notes real quick. Let me make sure. Yeah, just one last thing. If you do let it run rampant, the processes just kind of stack up upon each other. And then when they get stuck waiting on each other, that's how the deadlock then occurs. All right, let me move on to my program. That's not what I want to do. Let me go to the actual program now that I have made. Okay, so the main thing I want to show you is this part right here. Is this the specific part that I'm looking for? No, there's multiple, but yeah, that's right. There is multiple because you have to keep safe on every single thing. Okay. Okay, that's fine. So here's what I'm going to do then. I'm going to talk specifically about this safe sequence and this safe sequence. There should be one more. Unless I'm crazy. I could be a little crazy. No, it seems. No, okay, that's it. It's just those two. Okay, so let's go back to the part I want to talk about. Let's start with this one. Okay, so this is my safety algorithm that is in my code. I have arrays in this where I have a work array that copies available and finish arrays to track which customers have finished. Um, let me see. I have a loop. I do. Well, yeah, obviously I have a loop. I have a loop through the customers, and for each one that hasn't finished yet, I check if need is fully covered by work, and if it is, I add its allocation back into work and mark it finished and record it in the safe sequence, which is then when the request then fully comes through in our output, which we will get to shortly. Um, if I don't finish the process, obviously, then the request does not go through, and then request is denied or it's denied. It depends on which thing it denies upon. It could be invalid, exceeds, not available. Uh, System would be left in unsafe state. Just depends on the situation. Okay. Oh, wait, was that the wrong safe? That might have been the wrong safe. It was the wrong safe. This is the safe that I was talking about. Please ignore my other safe. I don't know why I got it confused. Yes, I did. All right, it is what it is. Okay, let's go to right here. Yeah, this is where request resources is. This is where it gets used, safe and unsafe. When a request comes in, I first check it's not more than the customer's declared need. Because if it is over its need, exceeded maximum, not available. If there's not enough resources, not available. And if it's perfectly in line, the request is granted. If it's not in line and the processes don't finish because it's either, you know, um, not good or not following through with all the processes, it is then denied. Okay, now comes this part. Now we're actually going to run the code, and I'm going to give you some real quick examples of how this works. Okay, so let's do this one. Right Q. I have it written down here because if not, it would be impossible for me to be able to just remember all of my outputs here. Okay, so this request is granted, and you can see the safe sequence it is found. That's proof that the safety algorithm ran and confirmed every process could still finish for this specific customer. Okay, move on to the next, which is Q 2 1 1 1 1. Okay, so now this customer exceeded the maximum claimed. The request is denied, which means unsafe. So the system would be left in an unsafe state. This command here that I'm going to do is going to show the full state, available, maximum, allocation, anything that's needed. And then that's all of my commands for the unupgraded version of the code. So let me exit. Okay, now we got to go back. There we go. We got to go back to here. Perfect. Now we are going to do the upgrade, which is displaying the safe execution sequence after every successful request, which is option A. So I'm going to real quick do this. That's not how you spell it, but whatever. It's all good. Simulator in C. I want to modify it so that let's see rhythm. Wow, I cannot type at all today. Jesus. Okay, could that get out of my way? Because whatever. Okay, perfect. Let me super quick change all of that. Okay. All right, give me a second while I add this upgrade in this part. Perfect. Sure this works. Okay. All right, perfect. That is the upgrade done. Back to this. Okay. Excuse me while I make sure that this is working. Okay, let me just double check that this works first before I start explaining, because I don't want to explain it and it's wrong. So give me 2 seconds here. Let me just make sure everything is running properly. Two, 0, 3, 1, 2, 1. And there we go. Perfect. It worked just exactly how I wanted it to work. Okay. Now, where is, put it here somewhere. Hold on a second. And here we go. There we go. I think that's, yep, perfect. Okay. So, pretty much, uh, this function just now the upgrade, what it does is it pretty much just walks through the safe sequence array that I built and it prints it out. Very simple. That's the order the algorithm proved every process the request can finish in. So process all of these processes here are its safe sequence. So it was granted and it's the system's in a safe state. Um, this line is the actual proof of safety. It's not enough for the algorithm just to say yes, it's safe. I'd want it. It's the whole point is to get the sequence of which the process is that it is safe in. Um, Compared to my original version before this upgrade, the program used to just say granted or denied with no explanation why. So it would just say this, it's in a safe state. It didn't say the safe sequence. So you never really knew why. And then if I were to put something that was not safe, the safe sequence wouldn't pop up because it's not in a safe state. Um, so since this is pretty much specifically this command and dealing with this safe sequence in specifically, um, pretty much by doing every command like this and then comparing it to the processes that it is safe in, it pretty much guarantees that you never run into deadlock at all. And that should be it. That covers Banker's algorithm. Thank you for taking the time to listen and watch and for paying attention. And thank you for any tips or comments that you might have for how it could have been more improved upon. Thank you for this, and I hope you have a great day. Thank you for watching.